and I'm very pleased to welcome Anna Franckowiak here. Anna Franckowiak is coming from the University of Bochum. She's a member of IceCube and doing a lot of very interesting work on both IceCube event analysis and all kinds of astrophysical analysis following up from that. And I think I personally met Anna first about a year ago at the month's meeting of different neutrino collaborations. And today we're going to hear about multi-messenger astronomy with neutrinos. So before I let Anna start, I would like to remind you to sign up for meeting with speaker and to come for dinner tonight. It should be available in the mailing list. So, and with all that, Anna, the floor is yours.
Thank you so much for having me. Yeah, so I'll tell you a bit about multi-messenger astronomy with high-energy neutrinos. And as Sasha mentioned, I'm from Ruhr-Universität in Bochum. And usually if I go abroad and talk about Bochum, no one has ever heard about it. So let me educate you about Bochum. So this is Germany. We are very far in the west. And if I talk to Germans about Bochum, they usually picture something like this. Because it used to be very industrial, but this was more like 50 years ago. Now it actually is quite green. So this is the large university. This is where my group sits, and there's a picture of us. While today I will talk about neutrinos, we also have a little campus observatory where we try to develop with those new modular design where we try to measure linear optical polarization on a large field of view.
Is that celestron C14?
Yes, that's what a celestron telescope. Yes. So the idea of this modular design, I mean, we can talk about this later. It will not be part of the talk. But yeah, I think it's a new thing that people, instead of going bigger and bigger, building even more bigger, expensive telescopes, people go to have this modular designs where they use relatively cheap telescopes that you can buy off the shelf, and you can with an array of those telescopes, you can reach sensitivity comparable to what you reach with the Zwicky transit facility. So I'm happy to talk more about the small telescopes later, but now I want to talk about multi-messenger astronomy. So the picture I have in mind when I think about multi-messenger astronomy is this of an elephant and blind men touching the elephant from different directions, and each of them only gets a very limited view of the elephant, and only when they talk to each other and basically combine their data, they have a chance to figure out that it's actually an elephant that they're touching. And I think the same is true for the universe with the different messengers and different wavelengths that we have to combine to get a more complete picture. And in addition to light, we have 3 new messengers, and those are high energy cosmic rays, high-energy neutrinos, and gravitational waves. And I will focus on the neutrinos, but they are closely connected to the cosmic rays. When I say cosmic rays, I mean mainly very high energy protons that hit us all the time from all directions. And what we can learn from them is that the universe has very, very powerful accelerators. So if you just look at the energy that we measure, so this is the cosmic ray flux scaled by some power of E, and the only point I want to make with this plot is that we reach energies larger than 10 to the 20 electron volts. That is 100 million times more than what we can reach with our most powerful man-made accelerators on Earth. So this tells us that the universe has very, very powerful accelerators. And it's obviously an interesting question to figure out what are those accelerators. And this is now where the neutrinos enter the game, because we can see the protons or heavier nuclei coming from those sources, but on the way from the source to us, they will be deflected by magnetic fields. So once we measure them on Earth, they do not point back to the source. But when they interact in the source with ambient matter or gas, they produce high energy neutrinos. Those are neutrals, so they travel straight to us, and they are only produced in those kind of interactions of high energy cosmic rays. So the neutrinos tell us where the cosmic ray source is located, and we still don't know what the source is. So we also need photons to tell us what kind of sources we're actually dealing with. So those three are basically very closely connected. So in this talk, I will now focus on high energy neutrinos. I will tell you how they are produced, how we can detect them, and what we can learn with them, or what we have maybe already learned from them. So when you think, or often when I talk to astronomers, when they think of neutrinos, they think about a supernova 1987A, where we have seen neutrinos, but those are, in my view, those are low energy neutrinos in the MeV range, and they are produced in nuclear decay processes. And those are not the neutrinos I want to talk about today. So the neutrinos connected to the high energy cosmic rays, they have energies 10 to the 6, 10 to the 8 times higher. And they're basically produced in cosmic ray beam dumps. So the ingredients you need to produce those neutrinos are first some very powerful proton accelerators that accelerate protons to very high energies, and then you need a target to smash those protons into. And then in those interactions, you can produce high energy neutrinos, and they typically then carry, on average, 5% of the initial proton energy. So let's look a little bit at the particle physics in there. So I told you we have the cosmic rays, the protons, heavier nuclei, they interact with protons or with photon fields. And what is produced mostly is pions in those interactions. And if you look at the charged pions, they will decay to a muon and a neutrino, and the muon will decay further, and in the end you get 3 neutrinos basically from the decay of charged pions. And well, you can put the same equation for negatively charged pions, but you also produce at the same time neutral pions, so roughly at the same level. And the neutral pions immediately decay to 2 gamma rays. So now you could ask yourself, if you want to study cosmic rays, you could just look at the gamma rays. Why make it so complicated and look at the neutrinos? And here the problem is that gamma rays are not exclusively produced in this kind of so-called hadronic processes involving high energy protons. They can also be produced by electrons in inverse quantum scattering or Bremsstrahlung processes. So if we really want to figure out what are the sources of high energy protons, then the neutrinos would be our smoking gun signature, because they are only produced in interaction of cosmic rays. So this is the maybe most important thing about the high energy neutrinos. So this is why we want to see them, but how do we actually manage to detect them? So the problem is they have a lot of unique features that make them really cool messengers, but at the same time, they're also very difficult to detect because the cross sections are so small. So you need a huge detector to be able to see them. You need roughly a cubic kilometer of detector volume to catch a few of those very rare interactions. And I'm a member of the IceCube collaboration. That is the largest currently operating neutrino telescope. It's located at the South Pole, and it has instrumented a cubic kilometer of ice in the very clear glacier located at the South Pole. So this is the surface, and we drilled holes 2.5 kilometers deep in the ice and then put in the instrumentation. So in the end, on the bottom kilometer of the cables that we put in there, we have a grid of more than 5,000 optical sensors that are able to measure a very weak light signal. So that's the idea of the detector. How does it actually look like if a neutrino interacts? So we do not see the neutrino itself. The neutrino has to interact, and then we see the secondary charged particles produced in the neutrino interaction. And there's 2 different channels how this can look like, depending on the way the neutrino interacts. So this is probably the most interesting one if you want to do astronomy, and you get this so-called track signature if you have a muon neutrino that interacts and is producing a muon. So what we see here is a high energy muon flying through the detector, and it's faster than the speed of light in the medium, so it's producing Cherenkov light. So those colored dots you see here, each dot is one optical module that did register some Cherenkov photons at different arrival times indicated by different colors. And the difference here is at the microsecond level. And the different size of the blobs, then you can see here is how many photons were detected at the individual module.
Can I ask, so that in this case, the interaction occurs in the atmosphere, not in the ice, right?
In the ice, so it can
Oh.
either happen inside the detector or in this case also outside, and then the muon enters the detector. Yeah, so this is what we see here. I will come back to the interactions in the atmosphere that also play an important.
The left ones are also muon neutrinos, or are they electron neutrinos?
So this could be an electron neutrino or a tau neutrino, or it could be a muon neutrino that interacts in a weak current interaction, and then so basically the neutrino leaves, and then you kind of destroy the nucleus, and you see a shower. The shower has an extension, the particle shower that you produce, but the extension of the shower is small compared to our distance in the instrumentation, so we can't really resolve very well the shower, and then it looks more like a spherical blob. It's very good to resolve the energy because all the light contained in the detector, but it's not very good to measure the direction. And if we now want to do astronomy, the direction is important, so we typically favor this channel.
Yeah, you mentioned you're detecting directly the neutrinos, and most of them are muon.
So we detect the secondary charged particles. So what we see here is the muon, not the neutrino itself.
Okay.
The neutrino has to interact, and then we can see the products from that interaction.
Thank you.
So I will mostly focus on the muon neutrinos because they give us a decent angular resolution, and this is what we want when we want to do astronomy. Now our goal is to measure cosmic neutrinos. Here they could go through the Earth because they interact so rarely, and then what we see is they interact in the detector or close to the detector, and we see the muon shown here in green entering the detector, and this is what is producing the light. However, at the same time, we have a background of so-called atmospheric neutrinos, and we get those when cosmic rays hit the atmosphere, and they produce a particle shower with all kinds of different particles. But in the shower will also be neutrinos, and those neutrinos can do the same, like we cannot really distinguish them from the cosmic neutrinos that we want to see. So this is one part of the background that we see. But we also, on top of this, we have atmospheric muons that can enter the detector. So from the northern hemisphere, the Earth will be a shield for the muons. So the muons cannot make it through the Earth.
So the neutrinos produced from the cosmic photons roughly the same energy as the cosmic neutrinos?
So there is I will show this later, there is a difference in the energy spectrum,
Yeah.
but they overlap. So it is hard to disentangle that, but I will show the spectra later. So by energy is a way to try to separate those two. Yeah, but now we go to the southern hemisphere. The detector is deep in the ice, so we have 1.5 kilometers to shield it from the muons, but there's so many muons and they're so high energetic that some of them can make it into the detector, and then we see the muon, and we don't know, was this now just a muon produced in the atmosphere, or was it a muon produced by a cosmic neutrino? So if we look at the distribution as a function of the zenith angle, this will be the southern sky, this is the northern sky. So in the southern sky, we have this huge background of atmospheric muons, and then more or less isotropically distributed, we have a background of atmospheric neutrinos. And if we want to put this into numbers, so this is a lot of atmospheric muons. We have a trigger rate of roughly 3 kilohertz, so 3,000 muons per second. If we look only at the atmospheric neutrinos, we have roughly 1 every 5 minutes. But what we're looking for, the signal of cosmic neutrinos, is something like 100 per year. So we actually really looking for right, the needle in the haystack. So have we seen those cosmic neutrinos? And the answer, yes, we have seen them in form of a diffuse flux. So if we integrate everywhere in the sky, we see a signal of cosmic neutrinos. And now coming back to your question, if we look at the energy distribution, so this is the muon energy is what we measure, not the energy of the neutrino, but it's a proxy also about the neutrino energy, and then it's just the histogram that you see here. And this is showing only the northern sky. So we throw away everything in the south because we know we have this huge background of the muons. So we look only at the northern sky where the Earth is a shield for the muons produced in the cosmic ray air showers. And this is how it looks like. So there's some tiny residual amount of atmospheric muons shown here in orange, but they're really negligible. And then what we see in purple are the atmospheric neutrinos. And if we now look at very, very high energies, you see kind of an excess sticking out here. So there's more data than what we predict from the atmospheric neutrinos. And this is actually our signal of cosmic neutrinos. And then you can try to model it and get an extrapolation how it looks at low energies, but at low energies it's really buried in this huge background of atmospheric neutrinos, but at high energies it is sticking out. And this is one of the channels how with IceCube we have discovered this diffuse. Now you can also look at different channels and we find a similar result.
So how do you know they're cosmic neutrinos and just, you know, versus not understanding the atmospheric neutrino? Or, I'm sure there are reasons why you wouldn't get an excess from atmospheric neutrino.
Yeah, we believe that we understand the physics quite well that goes into the cosmic ray air showers, and we measure the cosmic rays, and then from this we can make predictions how the neutrinos would look like. Of course, we need to know the cross sections and things like this. I don't have a plot about this, so there's actually two contributions that go into the atmospheric neutrinos. They're so-called conventional and prom neutrinos, and one of them comes from the decay of pions. This is most of the flux that we see, and then there could also be the decay of charm particles, and they would decay faster, so they would have more energy. But we have pretty good models for this, and nothing can actually explain this. Then we also have another channel where we look only at starting events in the detector. And this basically allows us even to veto most of the atmospheric neutrinos, because, I mean, they could come and interact inside the detector, but they would usually be accompanied by muons from the air shower. So this would be another channel how we can suppress also the background and refine the sun. So this, I think, is a very, very solid, very significant result.
I also assume that atmospheric the atmospheric neutrino rates are well known from historical experiments as well. Just because, like, you know, they've been historical.
Yeah, I mean at this level, right? And then you extrapolate to the highest energy, because only now we can see them at high energy. Yeah, we had them measured before at lower energies, and we think we have a good handle on the processes.
So if you don't know which ones are the cosmic ones and which ones are the atmospheric ones, then how do you find the directions of the cosmic?
I will come back to this later. This is the big challenge. But yeah, this is just to explain you how we can try to see the neutrinos. So we have this cosmic neutrino, the diffuse cosmic neutrino flux discovered already in 2013. And since then is the big challenge. The most pressing question is now, what are the sources of those diffuse neutrinos? So let's start to look at our own galaxy. There's basically a guaranteed flux of neutrinos coming from our own galaxy, because we know that our galaxy is filled with cosmic rays, cosmic ray electrons and cosmic ray protons, and those interact with the gas and the photon fields in the galaxy, and they make the galaxy shine bright in gamma rays. So this is a map by Fermi showing the GeV gamma rays, and you see this diffuse glow. Those are cosmic rays interacting with the gas. Now we can try to disentangle the different contributions that go in there. Some of them are produced by electrons and some of them are produced by protons. So we can make maps showing the inverse complement Bremsstrahlung. This is what you get from the electrons, and the pi-0 decay is what you get from the protons. You can fit this to the data, and then this pi-0 decay map would be a good template to look for the neutrinos, because they would be produced in the same processes. We're still not sure what are the sources, accelerating the cosmic rays in our galaxy, but supernova remnants and pulsars are the best candidates that we have. So looking at the gamma ray data, we now have a template that we can use to search for an excess of neutrinos from our own galaxy. And you see this template here. And this is derived from a fit to the gamma rays, and for comparison, you see the optical flux here. Now we have to smear this with our instrument response function. You see it's not super great, so you see this much more blurry map. And this is now an input to a template fit, trying to look for this flux of high energy neutrinos. And we find an excess from our own galaxy at 4.5 sigma level. And we can compare now this flux that we measure from our own galaxy to the diffuse flux, and we find that it's roughly 10%. Okay, so 10% of the diffuse flux comes from our own galaxy, but then we still have the remaining 90%, and we believe it's extragalactic. We still don't know what the sources are, and hopefully answering your question.
Is the galactic component the same energy neutrinos, or is it a different energy distribution?
We measure the spectrum, and it is a bit softer than,
Okay.
what we see. And it's only 10% of the total diffuse flux.
Right.
Yeah, so now the challenge is to find the remaining 90%. I want to show you 3 different strategies how we can try to basically find this needle index. So we can look at this huge number of neutrinos that we measure, mostly atmospheric, but there should be also a signal buried in this. And we expect the signal to come from distinct sources. So we could try to look for hotspots in the neutrino sky. This would be one method. We could also make an educated guess and say, oh, we think it's gamma ray blazars that are producing the neutrinos, and then we could look for an excess from the position of gamma ray blazars, for example. So we would only look for neutrinos from a certain source population, or we go here and focus on this high energy excess, where the probability actually that, if we look at an individual event, we never know is this atmospheric or cosmic neutrino, but we can assign a probability to it. And roughly above 100 TeV, we have maybe a 50% chance that this event would be cosmic or background. So we can use this stream, roughly 10 per year, and try to look for electromagnetic counterparts from the direction of the neutrino. So I will show you now examples for all of those different strategies. So the first one is probably the most obvious one. You take the entire data set of neutrinos and you try to find an excess somewhere in the sky. Let's say there's 3 bright sources. You should probably see this in the sky. However, this is how it looks. So again, this is only using the northern sky to suppress the background of muons entering the detector. And what you see here on the color scale is the local p-value. So that tells us the probability that an excess in that direction, if this excess is produced just by background fluctuation. So you want the p-value to be very, very small to have a large excess. And so this little point here shows us the smallest p-value, so the most significant excess that we see in the entire sky. And if you only look at this p-value, it's at 5 sigma level. So it looks very interesting. But this is the local p-value. Now you have to correct for the fact that we have looked in many, many, many positions of the sky, and this gives us a huge trial factor, or astronomers, we call this the look elsewhere effect. And once we correct for this, the 5.3 sigma goes down to 2 sigma. So if we look only at the neutrino data, then it doesn't reveal what the sources are. So again, the challenge here is that we have all this atmospheric background, and we have a large trial factor if we look everywhere in the sky. So the solution for this is to reduce the trial factor.
I just ask you, so you showed a previous plot where you took the Fermi all-sky map and you involve it with a beam. But this is, I think, much more sensitive, this angular scale associated with the p-values here. Looks like a much, much finer angular resolution.
yeah, this is a very, like you observed this very well. This is because this sample is using only the muon neutrinos that have this nice track, show this nice track.
And there you
in the
get
detector.
exquisite angular.
And then you get pretty decent angular resolution. Depends a bit on the energy, but it's, let's say, 1 degree level or lower. However, the galactic plane is it's mostly in that region for IceCube where you have this background of atmospheric muons as well. So here it's mostly is a different event sample, not focused on the tracks, but focused on those shower events where we have poor angular resolution.
Thanks.
But this sample allows us to basically look also at the southern sky. Yeah, so here we only look at the muons basically to get the good angular resolutions. So the solution to suppress the trial factor is to look at a predefined list of sources. So if we look only at a few sources in the sky, then we have a smaller trial factor, and this is what has been done. And this brings us basically to the second strategy that not looking everywhere in the sky, but we look only at a given number of sources.
In the trial factor, is saying you looked at the sky and you're saying what's the problem, where it has the most excess, and you want to condition on the probability that you saw high neutrino coming from that direction. Is that equivalent statement to the?
So what we do is like we go everywhere in the sky, like on a grid that is smaller than our angular resolution, and then we calculate the p-value in every position.
At some given time, like you look at the sky.
This is integrated over 10 years of data.
Okay.
We have a similar search where we also look for a time-dependent signal, but then you have even a larger trial factor because you have the timing in addition to this. Yeah, so the way to estimate the trial factor, I think roughly you could say what is our resolution and then how many square degrees do you have in the sky? Probably something like 10,000. Yeah, so we want to reduce this number, and in order to do this, we have a predefined list of sources. So I don't know, some of you attended the previous talk. It's very important to do blind analysis. So we define the list of sources first, and then we open the box and look what is in that direction. And we selected a list of 110 sources. This number of 110 is motivated that if you have a local excess of 5 sigma, after trial correction, it will still be 4 sigma. Is one way to define the number of sources, and then we selected them based on their gamma ray properties, weighted with the sensitivity for the neutrino search. So we are not very sensitive in the southern sky, so we would probably not select any sources in the southern sky, but mostly in that direction where IceCube sensitivity is largest. And the gamma ray properties, because remember how the neutrinos are produced from the pion decay, so the some unavoidable gamma ray flux that should come with the neutrinos. So if we don't know what the sources are, this is probably a good strategy. Yeah, and now if we do this, we find the most significant candidate that's actually right on top of this hotspot that I showed you before. That is the galaxy NGC 1068, also known as M77, which is a nearby Seyfert galaxy, so an active galaxy that we see from the side through this dust torus. We find roughly 80 neutrinos. So this is basically a fit, right? And the number of signal neutrinos is a free parameter, and we find roughly 80, and the error is plus minus 20 on this, in the energy range of 1 to 10 TeV. So really in this range where we also see a lot of atmospheric events, and this is after trial correction for this 110 sources is a significance of 4.2 sigma. So this source is very interesting because it has 2 sites where you possibly could have the neutrino production. So that the AGN could produce the neutrinos, but also it's also a starburst galaxy. So the star formation could also produce neutrinos because you would have a lot of supernova producing cosmic rays. So at this point, it's not really clear where the neutrinos are produced.
They all can produce 1 to 10 TeV. Sorry, Sean. All those sources that you just mentioned could produce neutrinos which produce muons that indicate 1 to 10 TeV.
So in the starburst, we could probably, produce also neutrinos at high energies, especially in this range of fluid. So this is not even the highest energy that ice cube could see. So this has actually a pretty soft neutrino spectrum compared to the diffuse flux. And yeah, both of those scenarios you can find models explaining the neutrino emission. So now looking, we only saw this because we used the gamma ray information. And if we believe that those neutrinos come from the source, then it tells us that the source has to accelerate cosmic rays to around tens to hundreds of TeVs in order to get the neutrinos up to 10 TeV. So how can we learn now what is actually the site producing the neutrinos? We can look at the multi-wavelength data for this source. So this is shown here. This would be the neutrino flux. You see it's like dropping pretty rapidly. So it follows, if you describe it as a power law, it's e to the -3, so pretty steep. You can compare this now to the low energy radio, optical X-ray data, but most interestingly, you can compare it to the gamma ray data. And we see Fermi detected the source, and this is also why it was in the catalog. But it's not very bright, actually. It was in the catalog because it's a starburst galaxy. There's only a handful of starburst galaxies detected by Fermi. This is why it wasn't in the catalog. And at the highest energy, we have only upper limits. So if you compare the gamma ray and the neutrino flux, it's more than an order of magnitude between them, which is puzzling because, again, if you think about how you produce the neutrinos, they come from the pion decay. You have the charged pions decaying to neutrinos and the neutral pions decaying to gamma rays, and the flux should be roughly at the same level at the source. And so if we don't see the gamma rays, that means we have to absorb somehow the gamma rays in the source because they should be there, but maybe they don't make it out of the source. So this is, I will show you as an important constraint on where the neutrinos are produced and what could be the mechanism producing the neutrinos. So in order to get rid of the gamma rays, all the theorists looking at the source place the neutrino production site at the very center of the active galaxy. So inside of the so-called corona, which is a hot plasma in the vicinity of the accretion disk. And this would be a good site to accelerate the particles and for the protons to interact with. But then it would also, the densities would be sufficient to get rid of the gamma. So this is the idea, and that already tells us something about is it produced by the AGN or the star formation? And the other question we would have is, do all Cypher galaxies produce neutrinos in the same way? So let's go back to the multi-messenger picture. We have now collected multi-messenger data for this source. And we have the neutrinos, we have photons in different wavelengths. But in order to understand what is the elephant, we need also theory to make a model of the elephant based on the data. And there's many people looked into this. They all come to pretty similar conclusions, but I wanted to show you one in more detail. This is a very complicated plot, so let me try to guide you through this. Again, here in green, you see the neutrinos, and the gamma rays are the black data points here. And then this model has two contributions, the starburst and the AGN. And the starburst is shown in blue here. So it would dominate the ray emissions in here and also the gamma ray data. And then there's the AGN, or the corona in this case, that is shown in red. And this would dominate the non-thermal emission in X-rays. And in optical, you also see the galaxy on top, the optical contribution. But it doesn't contribute to the gamma rays, but it's producing the neutrinos. Okay, so this tells us that actually the gamma rays and the neutrinos are not connected because the gamma rays are produced by the star formation and the neutrinos are produced in the corona. And the gamma rays that would be produced together with the neutrinos, they are absorbed in the corona because you have dense photon field and you have photon-photon interactions absorbing the gamma rays. So we learn the neutrinos are coming from the corona and the gamma rays are coming from the starburst. Now the next question is, do all of the Seyfert galaxies, or is there a population of Seyfert galaxies producing high energy neutrinos?
That's a good question. So you've got this torus and there's a jet.
There's a weak jet in this source.
Okay, so something is accelerating the protons not along the jet because they have to be accelerated this way to give you the neutrino flux through the torus.
So it's not entirely clear, but probably the jet is not the source where the particles are accelerated. And it also doesn't contribute to the gamma rays, so that people looked into this. So what is accelerating the particles? So yeah, the acceleration happens either in the accretion disk or in the corona somehow. So there would be there's different models. It's either magnetic reconnection in the disk. Or it could be a stochastic acceleration of the particles. So you need a very turbulent magnetic field, and then you can accelerate the particles.
And you can really get hundreds of TeV out of that?
People claim that you can. And people also try to describe this with shock acceleration, but there's not really good indications that there are shocks. Yeah, but maybe now I come back to the Seyferts. So the next step would now be to look at the population of Seyfert galaxies, come up with a model, how much neutrinos each individual source would produce, and then try to find the signal from the population. And the model here is based on basically predicts that the neutrino flux scales with the intrinsic X-ray flux that would be coming from the corona. It's complicated to measure this X-ray flux because in this case we look through the dust torus, so it is absorbed and you have to correct for this. But this has been done for the population of sources, and then we tried to find a combined signal from the population, and unfortunately didn't find anything, excluding NGC 1068 from this analysis. However, if we step away from this model assumption, we can do just a catalog search where we look at each source individually and without tying them together by the model prediction. And if we do this, we find two additional candidates at 2.5 sigma level. So if this is true, that there are other Seyferts producing neutrinos, at least it tells us that the model assumption we have been doing for the so-called stacking analysis is too simplistic. Yeah, there are probably other parameters that have been fixed by the model that play a role and make the neutrino flux different from source to source, which wasn't considered here. And this model was tuned to explain the neutrinos from the one source that we have seen with a very, very soft neutrino spectrum. And we find another indication that this model is too simplistic because we found two very, very high energy neutrinos at 100 TeV energy in spatial coincidence with another Seyfert galaxy, NGC 7469. And this was work done by my student Giacomo. And if this association is also at 3 sigma level, if this is true, would tell us that somehow this source is different from NGC 1068 because it will produce a much harder neutrino spectrum going to even higher energies than what we have seen from NGC 1068. So here it's still an open question if all Seyferts host cosmic ray acceleration and neutrino production, then I guess with more data, we might be able to distinguish between the individual sources and learn something about the environment. But yeah, going back to our diffuse flux, we have 10% from the galactic plane. And if we look at NGC 1068, it can only contribute roughly 1% to the diffuse neutrino flux. So we still have a lot of flux remaining. And let's go to this third strategy, where we now focus on the very high energy neutrinos here. And in near time, we try to find the electromagnetic counterpart. And I guess it's also connecting to the question we got from Zoom. Can we find maybe a counterpart that's transient or variable, and we would miss it otherwise? So the idea is that with IceCube, we can at all times see all directions, and we can measure neutrinos at the South Pole in real time and select the most interesting ones, and then reconstruct the direction and send this information to the astronomy community. And then the idea is that everyone who has a telescope points in that direction and hopefully finds an electromagnetic counterpart. We have two different streams, the gold and the bronze stream. The gold stream has 10 events per year, and half of them we expect to be cosmic neutrinos, the other half is atmospheric background. And we send this information with a median latency of only 30 seconds. And the goal is to find an electromagnetic counterpart. The most exciting event one of the most exciting ones we found in this program was in 2017. This nice neutrino track event, almost 300 TeV energy, but by itself is not significant. It has a 50% probability to be of cosmic origin. But now we look in the direction of this neutrino, we find that there's an actually already known very bright gamma ray blazer. So now we look into the jet of an active galaxy, and we can look at the 10-year light curve seen by Fermi. There's like some gamma ray flares in the past, but really there's like very bright one that nicely lines up in time with the detection of the high energy neutrino. So now if we compare the chance, calculate the chance probability that by chance we have a flaring blazer in the direction of the neutrino, this is pretty unlikely. So this has a significance of roughly 3 sigma. And because this was a very high energy event, it would tell us that this source can actually accelerate cosmic rays to several PeV, roughly 10 PeV, to produce this high energy neutrino. Also, here was some effort to model the emission of the source. If we only look at the electromagnetic emission, you see the optical data, X-ray data, gamma ray data, and you see this typical 2-bump structure in the spectral energy distribution. You can describe this by a single population of electrons that do a synchrotron radiation. This would explain the optical peak, and then inverse Compton scattering of the same population of electrons with their own synchrotron photons would explain the second population. Fits pretty well to the data, but then you wouldn't have any neutrinos because you need the photons. You could try with a pure hadronic model where we try to explain all of the gamma rays with pion decay, but that model totally fails. So you have this black line here, you overshoot the X-ray data by 2 orders of magnitude, but you would have a lot of neutrinos shown here in red. The solution, if you want to explain the electromagnetic data and the neutrino data, would be a leptohadronic model where you have electrons and protons, and that could look like this. So you can explain all of the data, but most of the gamma ray data actually explained by the electrons. So it's inverse Compton scattering, and there's only a small contribution that becomes important at TeV energies and then in the X-ray realm. So also here's somehow an indication that the X-rays might actually be very important to trace the neutrino flux. Here we can ask the same question. Do all of the gamma ray blazers produce neutrinos? And we can test this by taking the entire catalog of gamma ray blazers from Fermi and now look only at this position and see if we find an excess. We didn't find an excess. So ruling out the gamma rays as a very good tracer for the neutrino emission. Then maybe gamma rays are not a good tracer, but I'm sure you've heard about Sasha's work, where he, instead of looking at gamma rays, he's looking at the radio flux of the core of the sources, and he does actually find an interesting correlation of the published neutrino alerts with the sample. But there's still some open questions because other groups did slightly different analysis and they couldn't reproduce it. But I think here also with in the future, we might have smaller uncertainty regions of the neutrinos, and that should hopefully finally answer this question if the radio flux is a good tracer. And then some people looked into trying to combine what we see from the cyber galaxies and what we see from the blazars. So this one is the source TXS that I showed you, and those would be some candidate cyber galaxies. And we see here the neutrino flux and the intrinsic X-ray flux, and kind of it looks like they nicely line up. So maybe actually X-rays would be a good tracer, and it would work for the blazars and for the cybers. Obviously, we need more sources to populate this diagram to actually confirm this correlation that was more or less found empirically here. So this blazar would also contribute only at the single source, right, contributes at 1% level. So there's still a lot of remaining unknown here. And let me briefly go about this. So what could be other neutrino sources? In general, we can distinguish them between accretion onto supermassive black holes. So this is what I showed you some examples for, but it could also be a single source doing a stellar collapse. So we talked about active galactic nuclei, and the gamma ray blazars are disfavored as the main source. Tidal disruption events that we also learned about in the previous talk could be possibly good candidates. We discussed gamma ray bursts briefly, but as I said, we did. This is a very easy analysis because you know exactly the time window where to look for the neutrinos, so you can really suppress the background. You're very sensitive, and we haven't found any signal so far, unfortunately. However, there could be a larger population of sources that are like not successful gamma ray bursts, but supernova with a choke jet, where we don't see the gamma rays but could still produce neutrinos. Also called interacting supernovas that explode in a very dense circumstellar medium, and then the ejector would crash into that medium and produce neutrinos. This you can imagine like a supernova remnant, but a much shorter time scale. So those three types of sources are so-called hidden sources because they're not writing gamma rays. They are basically absorbing the gamma rays internally, and you can discover them in the optical. So we have a dedicated optical follow-up program trying to catch counterparts for those sources in real time. And we found, so we do this with this Wiki Transient facility, is an optical survey instrument with a large field of view, so we can easily cover the uncertainty, the angular uncertainty of the neutrino. When we find something interesting, then we can immediately trigger follow-up observations. And this is also how we identified the gamma ray burst afterglow of this source that we call against the bow. We found one very interesting source by doing this. Robert Stein used to be a student in my group. He finds, so the neutrino came, then we triggered ZTF, we got this data, and then the beauty of ZTF is that we have a survey covering the sky every 2 or 3 nights. So we can go back to archival data and we quickly realize, oh, there was something going on in the past, a very bright source that our colleagues had already identified as a candidate tidal disruption event. So they had seen the source rising in ZTF. There's a search for nuclear events, like something that explodes in the center of the galaxy and is then a candidate for a tidal disruption event, and they triggered UV observations. And once the neutrino came, we had more follow-up observations. And we calculated the chance coincidence for this to happen, and there's a 0.2% level. And after this happened, we looked more also at archival data, and we find 2 more similar candidates. And in every case, the neutrino is a bit delayed with respect to the optical light curve. So you see the optical light curve here and the matching color. The neutrino typically arriving 100 to 300 days after the optical peak. So if this is true, then tidal disruption events are very efficient sites of neutrino production. It is a bit surprising because they're not so different from AGNs, and they're rare. So they have to somehow be much more efficient in producing high energy neutrinos.
Days.
The delay?
The delay is days.
Days.
It's like a year.
Yeah, So in the red case.
What's the link there?
There's the different models trying to explain it. So for the first source, we had actually late time radio data showing that it was actually increasing in radio even at late time. So there is an inner engine that is still active even a year after the neutrino arrived. And there are like different models trying to explain the neutrino emissions, or either could come from the disk, there could be some jets or some outflow. And one idea is that this outflow interacts with the dust storms. And we actually see for those events, I don't think I have a plot, but if you look at the infrared emission, you see a delayed peak. This is the so-called dust echo. So the optical emission heats the dust, and then the dust re-emits in infrared, and this is delayed. And the peak of the infrared emission actually nicely lines up with the time of the neutrino. However, to describe this, you need really high energy protons in the source for the infrared photons to be a good target to interact with. But this could be one explanation why we see this delay in the neutrinos. Yeah, and one of the sources showed a second peak, which we found very interesting, because if it was just a normal tidal disruption event, the star should be gone, you wouldn't see a second peak. So maybe this was a tidal disruption, a partial tidal disruption event, showing a second peak. And yeah, let me finish with how we can improve this in the future. So like finding those coincidences obviously largely depends on how good can we constrain the direction of the neutrino. So typically it's several square degrees, and we are those two have worked very hard in testing new reconstruction algorithms to reduce this uncertainty area. And we actually succeed with new algorithms to reduce the area by a factor of 4 to 5. This is what we already have implemented in real time. And now we go back and reprocess all the old data, and we'll publish a new catalog with those improved uncertainties. And here you can see the distribution of the uncertainty area. So the 90% uncertainty area of the angular reconstruction is roughly 1.2, 1.3 square degrees. So this will give a new opportunity to people like Sasha to go and redo their correlation analysis with a given type of sources, but now with much better sensitivity, because those areas are smaller and more precise. And another improvement, obviously.
So what are the position uncertainties in gamma rays for Fermi? Is it same order, or is it much better?
Better. It's much better.
By an order of magnitude?
I would say by an order of magnitude. Okay. If you look at a single photon, then it's kind of the same, but okay. Usually if you see the sources in Fermi, then there's many
photons. I see.
So you get a much better resolution here. Yeah, and in parallel, there's new detectors being built. So I mainly focused on IceCube at the South Pole, where we're now planning IceCube Gen 2, which will be 10 times bigger detector. There's a detector under construction in the Mediterranean Sea, KM3net, and it's already taking data with the partial detector.
Some news report about KM3net.
Yes.
They have beaten IceCube, highest energy ever.
They claim they detected a 200
What do you think?
TeV
yes.
neutrino event. I think it's very interesting. And it looks like they did a very thorough analysis. The question I'm still puzzled about is how can it be that they have seen such a high energy event with the detector 10 times smaller than IceCube in half a year.
Period, yeah.
Yes, why with IceCube in 10 years we haven't seen this? I mean, the explanation could be that they were very lucky, like the neutron star merger, right? Okay. We've seen one, we haven't seen another. But maybe they would think there should be a population of these sources. Maybe it makes sense that we didn't see this particular source, but there should be others in the sky. And it's a bit surprising that we haven't seen it. But I'm not saying it's wrong. I'm very excited about this high energy event. And now I think we have to figure out what could be the source. In like Baikal, there's another detector under construction, and then there's plans for having new detectors basically everywhere in the world, using either this in ice or in water technique that I have showed you when you see the Cherenkov light, but there's also new techniques expanding the energy range to a very high energies, usually based on detecting the radio emission from the neutrino interaction. Yeah, there are even crazy ideas going to the moon or using forests actually as a detector for cosmic rays on the neutrinos. So we have a larger detector, new size and new technologies, making the detection of neutrinos better in the future. So in summary, I think neutrinos play an important role in this multi-messenger picture, and I think we, at the very start of neutrino astronomy, that we have a few source candidates identified, but we still don't really know what is the main contribution to the diffuse flux, and hopefully in the next years we will learn this, and who knows what the sources will be.
So going back to 1068, so do I understand correctly that the reason it was initially looked at was because of the gamma ray, but in the end it turned out the gamma rays had nothing to do with the neutrinos? Is that right? Because it's associated with the star formation.
Yes, yeah, it may be because of this slide. Yeah, it was initially so the source selection was done in a way that a lot of lasers were selected because of the brightest gamma ray sources in the sky, and then in addition, all the star-forming galaxies that were detected in gamma rays were also added to the list of stars. But this was done in a blind fashion before we looked at this. And yeah, you're right. It turns out that the gamma rays receive, that the neutrinos actually do not come from the star formation.
Sure. So I have a different kind of question. And I'll first ask, how much did IceCube cost?
300 million.
Okay, so we spent 300 million to go to the South Pole to build this detector. And I'm seeing a lot of 2 sigmas and 3 sigmas and 4 sigmas. And there's a detection of a diffuse background.
So I think we have 2 major milestones. Right? The
Yeah.
detection of the diffuse flux, that was only possible with the cubic kilometer detector, and the galactic plane. And behind this, we are still looking at candidates.
But I guess my main question, and we could debate the impact of those results, but I think they're great. But what launched IceCube? In other words, what was the science case before you had these results? In other words, what convinced the National Science Foundation to pay $300 million to build this? There must have been an amazing science case.
Well, look for the neutrinos. Like we haven't, before IceCube, we didn't see a single cosmic neutrino. Right? So with IceCube, we saw the cosmic neutrinos more or less at the level where they were predicted, the diffuse flux. So there was this prediction by Waxman and Bakal, they predicted it more or less there. And now it's the next step to find the sources, right? But maybe nature is not doing us a favor. It could have been gamma ray bursts and we would have seen them now. So I think it's making an important contribution to the field of astroparticle physics, to cosmic ray physics, to try to figure out.
I guess what I'm saying is, did IceCube meet the expectations? In other words, you must have laid out in the original proposal, here's what we might find, here's what it will mean. And now that we have the results, how do you compare them with what was written in the
actual
proposal?
proposal was like, I guess before I joined the collaboration, but I mean, I think it was measuring the diffuse flux, because for this we had predictions, and then there were all kind of model predictions for AGNs for gamma ray bursts, and some of them we could rule out, which is an important result.
Some of them we
and
can
there's
rule out. Some of them we can rule out.
Yeah, a lot of the optimistic models predicting neutrinos from GRBs, for example, and also the prime candidates when IceCube was built. We can constrain the model parameter space of those models. a lot. And then there's a whole lot of particle physics we can do with ice cubes that I haven't covered today. We measure neutrino oscillations at a level competitive with other experiments. We can set limits so far on dark matter, on exotic things like magnetic monopoles. Plenty of things you can do. Cross-section measurements at high energies. We also are part of the SNEWS, the supernova early warning system. So if there would be a galactic supernova, we would see it like we would see millions of neutrinos at ice cube. We would not measure the direction, but we would have a beautiful light curve because we have very, very good timing.
Have you seen that?
There was no galactic supernova since ice cube was but it could happen tomorrow, right? And then we prepare.
Yeah,
Probably the final question.
okay, sorry. So you started off by saying, how do we make these neutrinos?
Keeps
And
muting me here, so it's hard to talk.
you've silenced him?
Yeah, so let me know if you could meet at 3
Right,
p.m.
so you need high energy cosmic rays, basically.
Yeah.
Bombarding something, protons. And the prediction from that channel is you can make high energy neutrinos, but you will also make gamma rays, right?
Yes,
And then you come up with this puzzle. You're seeing the neutrinos, but there's no gamma rays coming from those particular objects. And so now we are scrambling and finding ways to hide the gamma rays because there's no way that they can be absent. So, I mean, people must have thought, isn't there any other way of making neutrinos that, maybe doesn't produce all that much gamma rays? Is there any other exotic formation mechanism instead of making this excuse? Should be there, but we don't see it. Yeah, and this is why.
so Ramesh, we do see it. This Fermi GRB is 145.
Doesn't
There's
exist.
certainly exotic ways to
Okay.
maybe make the neutrinos, but they also have to be there.
They also
right?
have to
Because we
make
know
gamma.
that the cosmic rays are there. And we also observe gamma rays in some sources, kind of indicating that the energetics are sufficient to do this, right? And I mean, for me, the main question is we see the cosmic rays, they have to come from somewhere. And then they should also be neutrinos from that source.
And gamma rays.
But they could be those kind of hidden sources, right? Where you
It shouldn't be too surprising, right? We see the neutrinos from the center of the sun. We don't see the gamma rays from positron annihilation. Right, that's the point of neutrino astronomy, is that you can see inside the source. So that's the first thing we put in the body of the problem.
So, but these gamma rays, they probably come to us with other frequency re-emitted, right? Because they cannot just disappear.
Yeah, they usually cascade down to lower energies. And yeah, we should see them here, right? In the MEV range. So this is another motivation
We'll
to
have
have
place
an
to find it.
MEV instrument to
Yeah.
be able to see them. So this is what a lot of people predict now, that the MEV range is where we find the counterparts.
What if
of
we
the
don't?
neutrinos.
What if we launch an MEV telescope and don't find any of this counterparts? This is a last place to hide, right?
This will be the last.
And then we
I
go
will
to
ask
the-
my question again. Is there some other way of making these neutrinos?
We look for neutrinos from dark matter decay, and there are models predicting high energy neutrinos from this, and we look for them.
And in
Walk
that case,
galaxies.
there won't be gamma rays? Or will that also make gamma rays?
It depends on the channel.
On the matter, yeah.
You can build a model that does anything.
So yeah, let's go with the last question,
Okay.
and then we wrap it up.
Are there X-rays with which you can constrain the column density?
People are trying that for
Okay.
the cyber galaxies, right? Especially for NGC 1068, because it's viewed through the torus, is very difficult, and it's yeah, this is basically giving us an uncertainty in the model for predicting the neutrinos.
Mhm.
The expectation is it scales with the intrinsic flux, and you need to model somehow
Okay.
what's going on to get that.
Yeah, so thank you, everyone. And Anna will be here today and tomorrow, and please, and part of the day tomorrow. And also, please sign up for the dinner today as well. So thank you, everyone.
Thank you.
Yeah, I hope
Thank
to meet
you.
with you
Very
at
interesting.
3:30 tomorrow.